Today we have a nice topic, I think. We're going to speak about visualization, which is quite nice, and also compared especially to previous lessons, which were a bit complex from a technical perspective. I think this one should be somewhat easier. So let's start, as always, with a quick motivation for why we even want to do visualization with programming, and why not just using off-the-shelf tools or existing softwares like, for example, Excel, which I suppose all of you know we can use to create some nice graphs. It has quite sophisticated plotting capabilities. So in theory, we could do all the analysis in Python, and then just maybe export the data, say, to a CSV file, open it with Excel, and then create some nice graphics, and we wouldn't need to bother with a new package to do all the plotting. But when we do that, I think there are some disadvantages where the most, probably the most stark one is the matter of bandwidth. So when we work like this, we actually lose the option to work in an interactive way, which is especially important when we do research and when we do exploratory research. So we want to try a bunch of stuff, we want to make some analysis, and then we want to see how it affects what we get right away without having to wait so much to download the data and then loading it in another software and do this long cycle. So keeping the iterations short between doing something to see what it does is very important. And also, like any software, even the most sophisticated ones like Excel, they will never be as flexible as just programming will be. So it is important to be able to do plotting in Python. And now we have to decide which kind of package we want to do the plotting. There are more than one package in Python that allows us to plot and create some nice visual graphs. So today we're going to focus on Matplotlib, which is like the standard in Python. So that's the most popular and the default option that people use. And we have decided to teach this one as the primary plotting library. Now, I will admit that it wasn't a completely trivial decision, unlike other packages, which really, I really felt like wholeheartedly that this was like the best option. With Matplotlib, I'm somewhat more undecided because it does have some shortcomings and disadvantages, as we're going to see. But it is quite a nice library. Like we said, it's standard. It provides somewhat like a Matplotlib-like interface. So like we saw with NumPy, for example, it's very much inspired by how Matplotlib works. So again, if some of you are familiar with plotting in MATLAB, I think Matplotlib will be familiar to you. And it's part of the entire ecosystem of Python. So it relies on NumPy. It has very nice integration with Jupyter, which is very important. So all the graphs we create, we're going to see them in our notebook, and they're going to be integrated nicely within it. And it also has nice integration with pandas. We're going to see that you can use all kinds of shortcuts within pandas to create graphs in Matplotlib with less code. So the main advantages of Matplotlib is, first, like we said, it's very common. So you have many users. And if you ask questions, it's relatively easy to find answers online, because many people have probably encountered this before you. It's a very flexible library. So if you work hard enough, there is virtually nothing you cannot do in Matplotlib. You can manipulate your graphics up to the level of a single pixel if you want. So you can really do anything you want, any kind of graphics you want, you can do it. And if what you want to do is rather simple and straightforward and something common, then it shouldn't be too difficult to do that. So very simple charts are simple to make. And if you work hard enough, you can also create some good-looking graphics that are definitely in publication level that you can put in your papers, which is important. But then on the downside, again, we're going to see that I think it's really overcomplicated many times. And the API is, at times, not even consistent. So it can be a bit annoying to get this package to do exactly what you want. It often feels like a little bit of a struggle to do that. And also the documentation. Like I think it has decent documentation, so you can find answers to what you're looking for. You can find many examples, but it could be better. So unlike, for example, in Pandas, where I said it was an amazing documentation and it's very easy to navigate, here it's a little bit more complex if you're looking for answers. And even though you can create complex charts, sometimes, again, it can be very difficult, and you will have to struggle with the package to get it to do exactly what you want. And this can be a little bit time-consuming, at least at the beginning, when you get to start working with it. And also, the default design, I think, is not that beautiful. So if you don't try to work a little bit harder to make the graphics look better, you will end up with somewhat mediocre-looking graphics. So you need to keep all of those things in mind. So there are other alternatives we can use to Matplotlib. I listed 2 options here. So there is Seaborn, which you can see an example here on the right. So Seaborn is actually based on Matplotlib, so it gives you some more high-level kind of interface. And by default, it has much better looking kind of design, more appealing graphics. But the thing I mostly dislike about Seaborn is that it couples the statistics and data processing with the visualization side. So some people may like it because, again, it's easier. You need to write less code, and you get the statistics and the visualization all at once. But I think that conceptually, it's a bit wrong. So it's better to think about those 2 things as independent. So you want to do data processing and statistics, and you want to do visualization. And if you combine the 2 and couple them together, sometimes you lose a little bit of flexibility of the kind of analysis that you can do. And also, it's more limited, I think. So there are some things which are very difficult to do in Seaborn. And you also have another nice library, which is called Bokeh. You can see some examples here. Again, it looks very nice. It has very fancy kind of graphics. And the nice thing about it is that it will provide you some kind of interactive plots. So it actually creates this JavaScript code that integrates into the browser and allows you to modify things in real time and gives you this nice user-friendly interface where you can zoom in and zoom out and start dragging things and move them around and see how it affects your graphics without having to write code. But again, both of these options, I think, are more limited. And that's the reason why eventually we decided to just stick with the standard here, which is Matplotlib. OK, so this lesson, we're going to go in a little bit different way. So instead of jumping to showing you code right away, I want to first start by covering this topic from a more conceptual perspective and try to understand all the different considerations for creating graphs and what different graphs we have and what are the reasons to choose one type of graphics or another. And I think this discussion really starts by knowing your variables. So understanding what is it exactly that you want to plot and you want to visualize. So all charts, essentially, what they do is illustrating relationship between variables. So it can be 1 variable, 2 variables, or even more. And the graphics give you some nice way to see those relationships. So before you choose the right kind of chart to create, you need to first ask yourself what are the variables. So how many there are, and even more importantly, what are their types. So when we distinguish between 2 primary types, we distinguish between numeric types, which get numbers, and categorical, which are just a bunch of categories, discrete categories. And for each of those types and each combination of them, we'll get a different type of appropriate chart. So if we have 2 numeric variables, for example, it will be appropriate to use a certain set of charts. But if we have, say, 1 numeric variable and want to see its relationship with the categorical variable, it may send us to a whole different set of charts that are appropriate to use. So that's really a crucial question to ask before you do plotting. And although most of the charts are two-dimensional, meaning that essentially we can stack in two variables, we can use all kinds of tricks to pack in even more. So we can use different colors and shapes and sizes to show even more variables within the same charts. So let's look at some different types of charts and try to understand all the important considerations and caveats and things to consider when you plot those charts and also when you look at them and want to interpret what they mean. OK, so let's begin with the most simple kind of chart, which is called the scatter plot, like you see here. Now, a scatter plot is very simple. I suppose you all know that. It's just a set of points, nothing more. Just you work with some x, y coordinates, and just within this, you put a bunch of points, each one representing one sample. And that's basically the end of it. Now, sometimes you can add those nice trend lines and other annotations if you want to the figure to convey even more meaning. And like we said, you can color code the points to pack in more data or change their shapes or size to include more data in your figures. And it's very important to notice what the axes stand for and whether they apply any kind of transformation, because sometimes it will be just a regular linear scale, but at other times it could be, for example, a log scale, which completely changing the interpretation of what you actually look at. And of course, it's only appropriate to use when all of the variables are numeric. So both the x and the y need to be numeric in order for it to be appropriate to use the scatter plot. And when you look at a scatter plot, it's also important to ask yourself, what do the x's stand for? What is the x variable? What is the y variable? What are the units? What are the transformations? It's very crucial to understand what each point represents. What is each record, each sample in this figure? Is it a person? Is it a gene? Is it a cluster? Is it some aggregate of different people? It could be all kinds of things. And of course, also important to understand what filters, for example, might have been applied to it. So if there was some filtering of, say, outliers, it's important to keep that in mind. Any questions? OK. Then we also have line charts, like you see here. Now, a line chart, you can think about it as just a scatter plot where you connect each two adjacent points. So these are very often called the markers. So you order them by, say, the x value. And then each two ones, you connect them with a line. And then you can see some kind of trend. Now, of course, it's appropriate to do that only if the y variable is believed to be some continuous function of the x variable. Otherwise, you will just get a complete mess, which doesn't really mean anything. So it's very common, for example, when x represents time. And this is related to the bonus presentation that you heard today. So if we have time series data, it makes a lot of sense to use a line chart with the x-axis being some timestamp and the y-axis being some value that we want to track its changes over time. Then we also have the bar chart. So for a bar chart, that actually shows the relationship between one variable, which is categorical, typically on the x-axis, and a numeric variable, which is typically on the y-axis. But sometimes you can flip it around, like you see at the bottom example. Here we actually have the categoric variable on the y-axis. And so we basically want to see the numeric value of different categories. And we can show few categories together by stacking them together. So here, for example, you can see that we have one category, which is G1 to G5, whatever it means. And then we also want to split it to men and women. So altogether, we have like 10 groups. And we can stack them together to get this nice-looking figure. On the bottom example, you can see that you can stack them in a different way. You can put them instead of side by side, you can put them on top of one another if there is some meaning to their overall summation. So if you want to see that their integration together has some meaning, it can make sense to put them on top of each other. And sometimes we want to also use some error bars, say, that can represent different types of uncertainty. So it can be some standard deviation or some confidence interval or something else that we want to see that we have some uncertainty about. And yeah, that's basically it. Another kind of graphics that is very common is the histograms. So a histogram is basically just a distribution of one numeric variable, like you see here. So the way this works, we take just one variable and we do what is called binning. We decide what kind of ranges of the x-axis will comprise a unique discrete bin, and then we take all the data points within this bin and we start counting how many samples fall within each bin, and then we just plot it. For each bin, we see the height of the histogram showing how many values are within this binning. Typically, they will be of the same width, but sometimes you can use uneven binning, like you see on the right-hand side example. And the y-axis, it sometimes will be just the raw counts that you get, or it can be normalized in some way. So when it's normalized, typically you will see that it's normalized such that the total area of the histogram should equal to 1. And that's important to understand that it's the area, it's not the sum. And that's especially important when you deal with unequal bin sizes. So that's a way to force it to being some probability density function. So the overall probability should be 1, and then you can see what kind of probability mass falls within each range. And here on the bottom, you can see that you can actually create histograms for even more than one variable. So if you do it for 2 variables, say, you can get a 3-dimensional histogram describing the distribution of a 2-dimensional variable. Questions? OK, on top of that, we also have density plots, which they're very similar to histograms in nature, and they're often based on them. Now, the density plot, unlike a histogram, tries to reconstruct some continuous density function. So whereas a histogram will have this discrete step-like look, so each bin will have its own value, the density plot will try to somehow smoothen that and show you an overall trend. So it looks nicer to see in the eye, and especially if you want to look at many different distributions and to compare them, it can be much more much nicer to look at density plots, because if you try to put, say, 5 different histograms on top of one another, you won't be able to see pretty much anything. They will just override each other. So density plots look nicer and they're more compact, but it has a downside. So the one important thing that is important to understand about density plots is that it's necessarily, by definition, relies on some kind of extrapolation. So that's already processing. That's already applying some theory on the data. That's not the raw values. That's not just pure samples. One moment. So typically that's done with kernels. So this is some kind of function that allows you to make assumptions. So the kind of density that you expect is some function of the samples that you have in its area using some kind of extrapolation function. And for example, we can assume that locally we expect it to be a Gaussian distribution, and then we can do this kind of extrapolation. But we have to make this decision and choose all kind of parameters before we can do that. Yeah, questions?
Isn't it exactly what we see down there? Is it a different binning for the same data?
Yeah, I think what we see here on the downside is different. Not different binning, but different parameters for the density for the same underlying data. And you can see that it can influence how it looks quite substantially. Yeah. OK. Another way, a nice way to show distributions, which is a little less intuitive to look on a first glance, but it is very, I think, once you get used to it, a very nice way to look at distributions, is what is called a cumulative distribution function, which is what you see here. So the cumulative distribution function, or CDF for short, is this kind of monotonic function that you see that always starting from 0, going up to 1. And that shows you like how the probability mass accumulates over your distribution space that you see on the x-axis. So what you see at each point, by definition, is the probability of having values which are lower than that value. So for example, you see here that for x around 15, we get 0.8, more or less. That means that roughly 80% of the values have a value which is lower than 15 within this distribution. Okay, is this clear? The nice thing about it is that unlike the density function, which requires us to do all kinds of decisions, this is always well-defined and doesn't require any kinds of heuristics or decisions. We can just take the data and plot it according to this definition, and we will get this nice-looking curve, which is more compact and conveys all the information about the distribution. OK, so in this example, you can see we have in blue the density function of some Gaussian distribution, and then on red, you can see the CDF of the same distribution. Now, if we want to look at the distribution of not a numeric variable, but a categorical variable, we can simply use a pie chart, which I suppose you all know. And we often put some values, which can be just row counts or percentages. Sometimes we do what is called exploding, so we take some parts and we make them stick out for some emphasis. And it can have all kinds of looks and shapes to it. And it is quite limited, so it doesn't allow you to do too much. Many people prefer to use other types of charts instead, like bar charts, which can convey more meaning. So bar chart can also show you the distribution, but also give you a more sense of like the relative abundance of different categories. And then another way to show a distribution, again, suppose you've all looked at it, is called a box plot, like you see here. So like histograms and density plots, it describes the distribution of some numeric variable. And that's actually a very nice and compact representation. So you can actually convey a lot of meaning just in one small box. So that's, I think, the main reason people like a box plot so much, because it's very compact and allows you to compare different distributions in a very compact way. So you can see the median, the second quartile of each group, which is often seen as this horizontal line in the middle of the box. And then the start and end of each box will typically be the first and third quartiles, Q1, Q3. And the difference between them, so the height of the box is often called an IQR, which I think is in the quartile range or something like that. And then sometimes you can also see the mean. So by default, most packages will not show it to you, but you can see it. For example, here on the bottom right, you can see that you have those dots in the middle of the boxes, and that's the typical way to represent the mean. So you can see if the mean is higher than the median or lower or about the same size. And then you also have this thing which pops out of the box at the top and at the bottom, which is called the whiskers. And that's actually not very consistent. So in different graphs, it can mean different things. And different packages will give you different things by default. So sometimes it's just the global minimum and maximum of the values. Or most commonly, it will be the lowest and highest value within 1.5 IQRs of the Q1, Q3. So basically just the height of the box multiplied by 1.5 all the way to the bottom, all the way to the to the top until you don't have such extreme values, and then it will be trimmed. Or it can be based on some standard deviations, or sometimes it's just different percentiles. So it can be at the 9th to the 21st, or the 2nd to the 28th percentiles, and all kinds of different meanings. And also very commonly you see that values outside of the whiskers are sometimes plotted as outliers. So we will often see those kinds of discrete samples above and below the whiskers to see samples which are outliers. Okay? Okay, the last kind of plot I think I want to talk about is what is called a heat map, which is essentially a matrix of colors. So it's a way to represent matrices. And that's actually a nice way to represent some numeric variable which depends on two other variables, and typically it will be discrete variables, although it can also be numeric and even continuous, which you can see. And that's a nice way to avoid 3D graphics, because if we want to do some, say, a density plot for one numeric variable depending on two others, we'll end up with some three-dimensional mesh in three-dimensional space. But if we use some color scheme, we can avoid it altogether and just end up with a heat map, which is nice to look at because it's two-dimensional. Now, when you do a heat map, I think one important decision is what kind of color map you use. So for example, at the top you can see that we have a quite simple color map with just 3 colors, red to blue through white. Or you can have much more colorful heat map like you see at the bottom with the full spectrum of the rainbow. And I actually want to encourage you to use the former, the simpler kinds of color maps. I think it's much more intuitive to look at those kind of heat maps, that you understand right away what is high and what is low. If you look at this kind of thing, you will have to go back and forth between the heat map to the color map to understand like what each color actually means. And it's very non-intuitive, like to understand which is high and which is low on this kind of scheme. Now, it's very commonly used for those kind of similarity or distance matrices. So if we want to see, say for all the genes, how much they are similar or different than each other, then we can create a heat map with the genes on both axes, and each color will represent a similarity or difference between a pair of genes. It's also a very common way to represent gene expressions. So we can see how the expression of different genes and samples look like. So we can have, for example, the rows corresponding to samples and the columns corresponding to genes. And we can see some normalized gene expression value. OK, and there are many more types. So there is, for example, an area chart, which is like a line chart, but with some stacking on top of each other. We have the radar charts, which again, like line charts, but with a circular domain. So that typically makes more sense if you have the x-axis having this kind of natural cycle to it. So maybe it represents, I don't know, the phases of sales cycle, or it stays in the week where you want to connect Saturday all the way back to Sunday or something like that. But people sometimes abuse it and use it for things which are clearly not circular, just for I think because it looks nice. But there is no reason. Also maybe because it's more compact. But I think it makes the most sense if you use something that is circular by nature. And likewise, you have the Polat chart, which is corresponding to a scatter plot, again with a circular domain. You have the Violin plots, which again, I think very nice. They also convey a lot of meaning. That's a combination of density plots with box plots. So that really shows you a lot of information about the distribution of different variables. And that will show up in an upcoming bonus question. And you can sometimes combine all kinds of plots together. For example, you can have a scatter combined with a histogram. And then you can see 2 variables through a scatter plot and the marginal distribution of each of these variables through a histogram, like here. And in any graphics, we can add more visual aids. So we can add, for example, some text and arrows to emphasize different parts. We can use lines, so trend lines, or just horizontal lines to emphasize different values. Very often we use those confidence areas around the trend line, like you see here. So a lot of way to augment the visual aids. Now, a few general caveats which are important to keep in mind every time that we deal with graphics is, first, it's very important to think what we want to do with those outlier values. So it is legitimate sometimes to get rid of values if they cannot really be accommodated within some graphics that we want to create. Say if all the values are within a very strict range of, say, 10 to 20, and then we have some very extreme value, which is 10 million, if we put it into the graph, it will completely distort the kind of scale of the graphics, and we won't be able to see anything other than this cluster of regular points and this outlier. So in this scenario, it can make sense to take it out so we can actually see what's happening within the data. But sometimes it's not a legitimate thing to do to remove just outliers. For example, if you just see a point that doesn't fit the overall trend, and there is nothing wrong with it, it was properly sampled, then removing it is like trying to mislead the viewer of the graph. There is no reason. It can be accommodated within a graph. Just because it doesn't really match your hypothesis is not a good reason to get rid of an outlier. And anyway, if you choose to get rid of an outlier, it's very important that you indicate it, for example, in the caption of the figure. And the same rule, I think, goes for data transformations. So again, it can be completely legitimate to use a log scale if you really have, if you want to display values which are many orders of magnitude in range. But you won't do it just to make your graphics look nice and show as if there is a trend where there isn't. And if you do that, it's very important to very clearly indicate that. Say in the label of the axis to say, OK, we have a log scale here. You should know when you interpret this graph that that's not a regular scale. And it's also important to keep in mind when we look at graphs that size can sometimes be misleading. So it's very easy to see patterns where they don't exist. And it's important to combine those visual aids with more rigorous kinds of analysis and statistics. And that's a topic we're going to cover in future lessons quite a lot. So you already started to encounter that in the exercises, and we're going to talk a lot more about how to do that. OK, so let's just get started with code. And I just put you some nice links here that you can use. So on the first link, I put you the example gallery of the Matplotlib, which is very nice. They have like many dozens of different examples for all kinds of graphics. And that's actually a very nice way to navigate through this. So whenever you want to do some graph and you're not sure how to do that, it's very easy just to scan and take a quick look with your eyes at different examples. And it's very easy to see that way if it looks similar to the thing that you want to create. And it's very easy to start that way, to actually start with a working example of something that more or less looks like what you want to create, and then just to modify that and make this example to accommodate your data. I also put you a link to the user's guide and the API of the library here. OK, so let's start to see how it works. OK. We begin with the regular imports and settings, as always. Now, the common way to import Matplotlib is using this line that you see here. We import the pyplot submodule, which is the main access point to this Matplotlib library. And we shorten it to plot, to PLT. So let's see a concrete example right away of how we can work with it. So what we have here is we use NumPy to first create an X range. So we just get all the numbers between 0 to 5 with jumps of 0.1. So it should give us like 50 or 51 values. Because here, 0, 0.1, 0.2, 0, all the way to 4.9. And then for y, we just take say, the sinus function of this using this vectorized function. So again, the y would be an array of the same size, just with the sinus values of those x values, like you see here. And then to create a simple line chart, we just use the plot function of the PLT module that we imported. And we give the x values and the corresponding y values, and that's it. You can see it creates these graphics, and it takes all the x and y pairs from these two arrays. Okay, very simple. Now we work in Jupyter, so whenever we start creating graphs, you can see it embeds very nicely into the notebook right away without us having to do anything. If you work in a non-interactive mode, so you can turn it off in Jupyter, or more commonly if you work in another environment, if you work, say, work in an IDE, then it won't show you right away when you start writing the code. You will have to use the show function by the end of the coding. So when you finish creating a graph, you will have to use the show function to actually show it. But we work with Jupyter in an interactive mode, so we don't need it.
Why is it not discrete, the graph?
Why it's not? Okay, good question. Why is it not discrete? Because we have some 50 values, and so you should see like 50 different markers, right? But 50 is good enough resolution, so you don't see it. So when you connect the lines, it shows discrete. But if we made it by jump, say, of 1, okay, you see that it's actually discrete. Okay, just we had a good enough resolution, so you didn't notice that. But it's always discrete. Even the line charts are discrete. And now in some older versions of Jupyter, you had to use this kind of magic command to actually create this inline view. If you didn't do it, you were by default in the non-interactive mode. But now in newer versions, I think that's the default. So in Python 3, I think that's the way it goes anyway. And like we showed, you have this interactive viewing of your graphs. OK, now before we actually start seeing how to create all of those different graphs, there are two important concepts that are very important to explain right away, and those are figures and axes. So let's understand them through this example. OK, I'll create a nice resolution again, because all the graphs are now ugly. OK. OK, so what are figures and axes? So a figure is basically just an image that you're trying to create. So if you were to work outside of Jupyter, a figure would be like something that opens in a separate window, and then you can save into a file in some format, like a PNG format, JPG, any format you like, you can create a figure. So that's like everything within one image. For example, here in this example, I created two figures. There is the upper one, which you see here, all of these together. So these two and this one too. And then there is the one on the bottom, which is a separate figure. Now, again, in Jupyter, you don't very clearly see this distinction. So they just show up one below the other. But in theory, I could have created all of those different parts as one figure, and you probably wouldn't even notice the difference. Now, within each figure, you have what is called axes. So these are those nice rectangles that you see here. Each one of them is like a different space for a different kind of plots. So basically just x, y-axis, and that's why it's called the axis. And for example, in the first figure, you see three of them. So you see this one here, and you have this one with the green line. And then you can see also a third one with the orange line, which actually overlaps with the second one. So they can overlap and be on top of each other or within each other. They can be anywhere you want, but each of them is like a separate entity that can show its own graphics. And now within each axis, you can also show as many graphs as you like. For example, here on the first axis, you can see we have two different plots. We have the red curve and we have the blue curve. Okay, so that's as far as definitions go. Now let's see with the code examples how we can create those figures in Access. Okay, so the most basic way to create a figure is just to use the figure function within the plot package. And you don't have to specify any values, but here we want to make it of different size. We can specify the figure size, which is given as a tuple, where the first one is the width of the figure, and the second one is the height of the figure. And I think it's with inches. I think that's the measure they use. And now if you want to create an axis, there are many ways you can do it. One way is to use the subplot function, which is a nice way to split your figure into evenly sized segments, each of which becomes its own different axis. So for example, here we want to have one row and two columns. And we want to have two axes of the same size, each taking another half, a different column within the overall figure space. The way we do it is we specify first the number of rows that we want, so just one in this case, and we want two columns. And I want that axis, the axis 1, to be the first out of two. And notice that it's a 1-based index. So that's the first. And then x2 will be the second one. Or we can just specify it by explicit coordinates, like you see in the third axis. And that's using the addAxis function, which should get 4 numbers. So I think it's like the x offset and the y offset. So you can see it should be like 69% to the right and 66% upward. That's like the bottom left corner of this axis. And then the width is like 20% and the height is 20%, and that's what you see here. And then this creates this nice rectangle which you can work with. And now if we want to create plots within of those figures, we can just use the plot function for each of the axes. So if we do x1 plot, we will get something within axis 1. And then again we use x1, so we get a second plot also within the first axis. And then when you use the second and the third, so on. So all of that is the first figure that you see. Then we can create a second figure, again using the figure function, and now create a subplot. We use 1, 1, and 1 because we just want the axis to be the entire figure space. And yeah, and then you can plot on that, and you can see the gray curve here. Any questions? Okay. And you can see that the types are indeed something like what you would expect. So you can see the first figure is a figure type. And the axes are different kinds of axes. So the first one that we created using the add subplots is a subplots kind of axis. And the third one is just a simple axis. So not exactly the same types, but they do have like the same functionality, no matter how you create them. We can use the subplots to create any grid of axes that we want. So for example, here you can see we can create a grid with 2 rows and 8 columns. Sorry, 4 columns, so 8 axes altogether. And within each of them, we can create our own graphics using a simple for loop. So let's see how it works. We can actually use the subplots function, which is of the plot library, which I think is a nicer shortcut to work with. So this gives you the figure and the axis together right away in the same function. So you specify the number of rows, 2, and you specify the number of columns, which is 4. And you can specify the figure size. And then it creates for you a figure and this thing, which is called the axis. Now, if we look what's the type of axis, you can see that it's actually nothing more than a NumPy array of type object of shape 2 and 4. So it's 2 rows and 4 columns, like we asked for. So it creates this NumPy array of axes where we can access each element within this array and get a corresponding axis. So we can then create this for loop, iterating through the rows and columns. And then when we access the I and j entry of the axis, we get an axis object that we can then use the plot function of to create this kind of figure that we want.